Okay, so we're now ready to do our mathematical analysis of the LC circuit, which we've discovered, in fact, is the LC oscillator. This circuit is an oscillator. And I'm going to do it frontwards now, just using 802 physics. And we'll see that we get exactly the same thing that we got using the extended analogy that we've explored over the past several videos. So I have an L and I have a C. This C has a charge Q on it. And to be consistent with the way I did things on the previous videos, I'm going to choose my direction of the current to go that way. You know from 802 that that was an arbitrary choice. I could have chosen my current to go this way, and that would mean that the answer that I would get at the end would have the opposite sign. But I'm going to choose my current to go this way. Notice that that means that when I is positive, Q is getting less, because I've chosen Q to be the charge on this plate, again, to follow what I did in previous videos. And that means that when I do the math here, I have to have that I is minus dq dt. Because when the current is positive, the Q on this plate is decreasing. Okay, so let's analyze the circuit. What do? I walk my finger around and I do the bookkeeping of how the potential or electromotive force changes. Let's start here. I walk my finger this way. I'm crossing this capacitor from the minus Q plate to the plus Q plate. That means that the potential goes up, and it goes up by an amount, Q over C. So I write down Q over C. I keep walking, I keep walking, I keep walking, I keep walking, and I get to this inductor L. And my finger is crossing this inductor L in the direction of the current I. And that means that I get minus. That minus is the sign from Faraday's law. That minus is the sign from Lenz's law. Minus L di dt. That's the EMF across the inductor. Keep walking, keep walking, keep walking, keep walking. I get back to where I started. And so that is equal to 0. That was the 802 analysis. Now I'm going to plug this equation into this one and replace I by dq dt with a minus sign. And so what I get is Q over C plus L d squared Q by dt squared is equal to 0. And look at that. I've got a second order differential equation, and it's an oscillator equation. How do I see that it's an oscillator equation? Well, let me just rewrite this in the way that I'm used to seeing oscillator equations written. I'm going to write it as d squared Q by dt squared plus 1 over LC times Q is equal to 0. And that is an oscillator equation. Same equation as when you describe a mass on a spring. So this is the F equals ma of my circuit. This is the differential equation that I get by doing the 802 analysis of walking around the circuit and keeping track of all changes to potential or electromotive force. And that turns out to be analogous to the F equals ma of my mechanical oscillator. Remember that when we did RC circuits, we ended up with a differential equation with Q and Q dot. And when we did RL circuits, we ended up with a differential equation with I and I dot. Now, when we do LC circuits, we end up with a differential equation with Q and I dot. And I dot is Q double dot, so I have a differential equation with Q and Q double dot. Second order equation describes oscillations. Voila.